Google's DeepMind, known for developing AlphaFold, which revolutionized protein structure prediction, has now introduced GNoME. This innovative AI tool is a game changer in AI, with the potential to uncover an astounding number of new materials rapidly. In this video, we're going to explore what GNoME is, how it works, and the massive impact it could have on material science and beyond. So, what's GNoME? It's an AI tool built for a groundbreaking purpose: uncovering new materials. Its full title, Graph Networks for Material Exploration, hints at its core function. It leverages deep learning, a branch of AI, to deduce the structure and properties of new materials based on their chemical components. Why does this matter? Materials are integral to our everyday lives, from the solar panels on our houses to the batteries in our phones and the microchips in our computers. Discovering materials that are superior, more affordable, or environmentally friendly. Traditionally, discovering new materials is a lengthy, complex process. Scientists often spend years experimenting with different elements to find the perfect combination with the desired properties. Even when they stumble upon a promising material, understanding its full potential and how to improve it can be elusive. This is where GNoME steps in as a transformative tool. It harnesses existing material data to forecast new discoveries. GNoME can rapidly evaluate whether a material will be stable, the energy needed for its creation, and its structural composition. Remarkably, GNoME can analyze millions of materials in a matter of hours, a feat that would typically take years. Both GNoME and AlphaFold, developed by Google DeepMind, employ deep learning, but for distinct purposes. AlphaFold focuses on predicting the structures of proteins essential for life, which consist of amino acids that fold in intricate patterns. GNoME, conversely, is dedicated to predicting the structure of materials, zeroing in on how atoms, the fundamental units of materials, assemble into various crystal formations. If this video is sparking your interest, hit that like button and subscribe for more cutting-edge updates. Stay tuned as we continue exploring GNoME's groundbreaking impact. Don't miss out. Your support keeps this content coming. What are GNoME's accomplishments to date? In a groundbreaking study featured in Nature, Google DeepMind and their partners revealed some astonishing findings. They deployed GNoME to predict the structures of about 2.2 million novel materials. This volume of discoveries is comparable to nearly 8 centuries of accumulated knowledge. But they didn't just stop with predictions. They also synthesized and examined over 700 of these materials in a laboratory setting, utilizing a robotic system designed for automatic material synthesis and characterization. And the results? They were impressive. GNoME's predictions turned out to be highly precise, boasting a success rate exceeding 90%. GNoME operates using two primary models. The first, GNoME stability, predicts a material's stability from its composition. For example, when given elements like iron and oxygen, it evaluates their potential to form a stable compound. This model employs a graph neural network, picturing materials as a network of atoms, the nodes, interconnected by chemical bonds, the edges. The second model, GNoME decomposition, calculates the energy required to decompose a material. It takes into account a material's composition and stability, like iron oxide, and determines the energy needed to break it down into iron and oxygen again. This model utilizes a transformer network, typically used for sequential data like text, to analyze the sequence of material components. Together, these models enable GNoME to assess a wide array of materials, from the simplest to the most complex, pinpointing the most promising ones for further exploration based on their stability and decomposition energy. To illustrate, let's consider some materials GNoME has identified. These substances, created and evaluated in laboratories with robotic assistants, are potential game changers for solar cells, batteries, and computer chips. Take copper-zinc tin sulfide, CZS, for instance. It's an excellent candidate for thin-film solar cells. Not only is it cheaper and more flexible than traditional cells, but it also excels in converting sunlight into electricity. GNoME's assessments of its stability and low risk of breakdown were verified through laboratory tests. Another standout material is lithium iron phosphate, ELFP, perfect for lithium-ion battery cathodes in electric vehicles and electronic devices. Known for its energy efficiency and durability, GNoME accurately forecasted its stability, a fact later corroborated by laboratory tests. Zinc tin nitride, ZTN, is poised to revolutionize the production of transistors for computer chips. It boasts rapid electrical conductivity and efficient switching between on and off states. Here again, GNoME's predictions regarding its structural stability and low decomposition energy were validated through lab experiments. GNoME's journey into unexplored material realms is a testament to the transformative power of AI. It's reshaping our understanding and capabilities in material science. If you're as thrilled about this technology as we are, don't forget to hit the subscribe button and like this video. Thanks for watching, and see you in the next one.